Yeah, so we're very happy to have Cynthia Vinzant here talking to us about log-concavity, matroids, and expanders. So please take it away, Cynthia.
Right. Yeah, thanks for inviting me to this super nice conference. I'm going to talk about work that's a year or two old, but I thought would be interesting to this crowd. And it, as the title suggests, concerns a connection between log-concavity, combinatorial objects called matroids, and expansion, edge expansion of graphs. So to start off, if you're interested in the expansion of a graph, then what you're interested in is whenever you split the graph into two subsets, say S and S complement, you want to know how many edges are in between relative to the smallest size of S or S complement. You want to take the minimum over all subsets of the vertices of this quantity. That's the expansion, the edge expansion of the graph. And you might be interested in this quantity if you're, say, running a Markov chain on this graph and you want it to mix quickly. This is a quantity that's related to the mixing time of that. And one way to get a handle on this quantity is through the eigenvalues of the adjacency matrix of the graph. So in particular for a d-regular graph, we can bound this using the second eigenvalue of the adjacency matrix. And so what you really want to do is bound if it's a d-regular graph, then d will be the top eigenvalue, and so you want to bound the gap between the first two eigenvalues of the adjacency matrix. And so I'm going to talk about this for a special class of graphs, namely the edge graph of polytopes, of special polytopes. So there's a conjecture by Milena Mihail and Umesh Vazirani that the edge graph of any 0,1 polytope has expansion at least 1. So you're walking around the vertices along the edges of a polytope. You want this to mix relatively quickly. And the theorem that I want to talk about is that this holds for matroid polytopes. So which are a special class of very nice 0,1 polytopes. So I imagine that this is familiar to a large portion of the audience, but I'm going to go through it quickly anyway. So for me, a matroid is going to come with a ground set of the numbers 1 through n, and will be defined through its independent sets, which will be a non-empty collection of subsets of 1 through n, satisfying two properties. The first is that it's closed under inclusion. So if I have an element of my subset and some further subset of it, that's the smaller one is also independent. So this makes the independent sets of a matroid into a simplicial complex. And the second is sort of an exchange property, that if I have two subsets that I'm calling independent and one is bigger, then I can pick an element that's in the bigger one and not the smaller one and add it to the smaller one to get an independent set. The maximal elements, the maximal subsets, independent subsets are called bases. And the second criterion implies that they're all going to have the same size, which I'll call the rank of the matroid. Some additional objects that one can associate all sorts of objects to matroids, but in particular, a matroid polytope will be a 0,1 polytope that I get by taking the convex hull of the indicator vectors of the bases. And for me, one object I definitely want to associate is a polynomial, which is just going to be the generating polynomial of the matroid. So this is going to be a polynomial in n variables. That's just the sum over the monomials corresponding to each basis. So one fundamental example of a matroid is one given by linear independence of vectors. So if I pick n vectors in some vector space, then I can get a matroid by taking my independent sets to be the indices of linearly independent subsets of these vectors, and the bases to be exactly the subsets that correspond to the bases for the span. And the rank will just be the dimension of the span, the size of the basis. And so for a very tiny example, if I pick 4 random looking vectors in R2, just the plane, then every pair of them will be linearly independent and form a basis for R2. And so my set of bases will just be all collections of the numbers 1 through 4 of size 2. If I take the convex hull of those indicator vectors, all 0, 1 vectors with exactly 2 1s, I get an octahedron in R4 that lives in a plane, all of the coordinates equal to 2. And the basis generating polynomial is just the second elementary polynomial and variables x1 through x4. So it's the sum over all pairs ij of the monomial xi, xj. And just as a non-example, so many things are not a matroid, but in particular, if I take the collection of subsets 1, 2, and 3, 4, then these will not form the basis for any matroid. I invite you to see how that would contradict this second criterion. Okay, that was crash course on matroids. And really what I'm going to be doing is studying matroids through this multivariate polynomial that I associate to them. And as a spoiler, it'll turn out that these polynomials have a property called log-concavity. So if I have some polynomial with non-negative coefficients, I'm going to say it's log-concave if either it's identically 0 or if log of f is concave as a function on the positive orthogonal. So it literally, its Hessian is negative semi-definite whenever I plug in any point in the positive orthogonal. And it's strongly log-concave if both f and any of its derivatives have this property, or log-concave. Where here I'm using the shorthand notation for taking any arbitrary derivatives. These have come up several times over the past years and gotten various names. So if you have a polynomial that's homogeneous and strongly log-concave, it's also called Lorentzian, which is in a paper by Peter Menden and Jun He. My favorite example of these is just a real-rooted univariate polynomial with non-negative coefficients. There, it's extremely easy to see that it's log-concave because you do the calculus exercise of taking log and taking 2 derivatives. And what you find is you get a rational function that's clearly non-positive whenever it's defined. And in particular, it will be non-positive everywhere in the positive real, everywhere away from the roots. So this shows that f is log-concave on the positive real line. And if you take the derivative of such a polynomial, then its roots will have to interlace the roots of the original, as I've tried to draw here. And in particular, they're all going to have to be real, and they're all going to have to be non-positive. So we get a polynomial of exactly the same form. So we could do the same calculation and find that it's log-concave. There are many other and arguably more interesting examples of these things. There's a multivariate version of real rootedness called stability, and these polynomials are strongly log-concave by a generalization of the Brun-Minkowski theorem. Mixed volume polynomials of compact sets, convex compact sets, are log-concave, strongly log-concave. And by recent work of Hu and Meseros, normalized Schur polynomials are also have this property. So lots of polynomials that that people care about, especially say in this audience, have this property. And one of the theorems that now has been proved by several collections of authors is that for an arbitrary matroid, the basis generating polynomial is strongly log-concave. And this was sort of not dependent on, but inspired by the work of Adepozito, Hu, and Katz and combinatorial Hodge theory. And I wanted to digest a little bit what this means and how one could use it or prove it. So log concavity at a point in the positive orthant, this is what we're requiring. Again, if we do the calculus exercise, what this says is that when we take the Hessian of the log and evaluate it at a point in the positive orthant, we should get something negative semi-definite. So this will be a real symmetric matrix. All of its eigenvalues should be less than or equal to 0. And if we write down what that Hessian is, what we get is we get f times the Hessian of f minus the gradient times its transpose, all divided by f squared. And then that whole thing evaluated at some point. And one consequence of this is, what is this? This is a constant times a matrix minus a rank 1 matrix, is how I want to read this, divided by a positive constant. And so what you can actually see from this is that the quadratic form, so this is a real symmetric matrix, defines a quadratic form, and it has to be negative. So this quadratic form has to be negative everywhere. In particular, then this quadratic form has to be negative on the hyperplane orthogonal to the gradient at that point, on which this will just evaluate to 0. And so in particular, one can check that means that this real symmetric matrix can have at most one positive eigenvalue. And in fact, if we start with a polynomial with non-negative coefficients, and we're evaluating the point in the positive orthant, then all the entries of this matrix will be non-negative, and so it'd have to have at least one positive eigenvalue. And so this is actually, it will have exactly one positive eigenvalue. And so just as an example of this theorem, so for our little rank 2 matroids, so we said that the degree 2 elementary symmetric polynomial in 4 variables is the basis generating polynomial of a matroid. It's quadratic, so when we take its Hessian, we just get a constant matrix. We get the following constant matrix, and we can write this matrix. So this is the all ones matrix, which is rank 1, minus the identity matrix. And so this is going to have exactly one positive eigenvalue corresponding to this, and then the rest will be negative. So this is what the theorem promises us will happen. And our non-example, it's not a matroid, but if it were, this would be the basis generating polynomial of the non-matroid. And we see that when we take its Hessian, we get a little block 2 by 2 matrix. And this will have 2 positive and 2 negative eigenvalues. So this polynomial f is not log concave. Yeah, and another way of saying that you have at most one positive eigenvalue is that the second eigenvalue has to be negative or non-positive. And so this is going to be a talk very much about the second eigenvalues of things. And so actually one can use these observations on the slide before to try and characterize strongly log-concave polynomials. In particular, if you have quadratic forms like the Hessians were on the page before, that take positive values on the positive orthant and are negative on some hyperplane, then any convex combination of these is also going to have the same property, is also going to be take positive values on the positive orthant and negative values on this hyperplane. And so in particular, is it going to again have this property of having at most one positive eigenvalue. And using these convex combinations, one can actually sort of build up a polynomial, or the Hessian of a polynomial from Hessians of its derivatives. And so in particular, just as a bit of notation, if I associate a polynomial with a graph that's just given by whose adjacency matrix is just the Hessian evaluated at the all ones vector. For the moment, let's not worry about weights on the edges, but just 0 or non-zero in terms of having an edge. Then we get the following characterization of strongly log-concave polynomials. So some polynomial is strongly log-concave if and only if the graphs associated with various derivatives of the polynomial are connected whenever they sort of have a chance to be connected. And also that whenever you take derivatives of a polynomial down to a quadratic, you take, if the polynomial is degree d, you take d minus 2 derivatives, then that quadratic polynomial as a quadratic form should have at most one positive eigenvalue. This is actually, so this is really an if and only if for strong log concavity. And a sort of very rough idea of why this is true is that if once you have this property for all of these derivatives, then one can take convex combinations of them to recover more complicated polynomials. And also, you know, if you have a homogeneous polynomial, then we also have that, you know, f times the degree is just equal to the sum of its derivatives for some specific one. And so one can build back up to f, or the Hessian of f, through its derivatives. Okay. So as promised, what I'm going to do is relate this to some Markov chains. So from a polynomial, a log-concave polynomial with non-negative coefficients, what I can do is take its Hessian, to say the all ones vector, and normalize it so that the matrix becomes stochastic. This normalization will not change the fact that the second eigenvalue is less than or equal to 0. And in particular, if I lazify the corresponding random walk, then the second eigenvalue will be at most a half. Let's leave alone for the moment the reason to do such a thing. But so for an example, if I take my favorite quadratic polynomial and I take its Hessian, then the normalization will just be scaling by a third. And when I take half times the identity plus half times this transition matrix, I get the following matrix. And I want to interpret the corresponding random walk in the following way. This gives a random walk on the numbers 1 through 4. And one way to think about this random walk is if I start at some singleton I in numbers 1 through 4, I could choose another element uniformly at random to add to it. And then of that subset of size 2, I can pick one of these numbers, one of the two numbers uniformly at random to drop. So this is going to give I, j, and I get rid of either I or j. And I claim that this is actually the transition matrix for this walk. If I start at an element, say 1, then my chances to moving from, say, 1 to 2, I would have to go from 1 to 1, 2, which happens with probability 1/3. And then I'd have to drop 1, which happens with probability 1/2. So then my transition probability is 1/6. But then, you know, there are many ways that I could end up going from 1 to 1. Namely, I can pick whatever I want here and then just drop it. So there are 3 different ways, all that occur with probability 1/6 in order to do this. And in fact, because this is the composition of, so this is taking sort of 2 steps in a Markov chain going between subsets of size 1 and 2, this matrix is actually positive semi-definite. All of its eigenvalues are going to be non-negative. You can write it as some matrix times its transpose. So all of its eigenvalues are non-negative, and its second eigenvalue is at most 1/2. So from this log con.
Oh, there's a question in the chat. Ben asked, in general, is this random walk corresponding to basis exchange in the Matroid?
So good, yeah. So I will answer your question. So this is where we're going. So this right now, this is only on a random walk on 4 elements, right? Not even on the 6 bases of this Matroid. But so one can do a more complicated version of this. Namely, so if we start with a simplicial complex that's pure of some dimension d-1, for example, the independence complex of a matroid of rank d, and we might allow some weights on the faces, which let's ignore for the moment. So what I'm going to do is define a random walk on delta k, so the faces of the simplicial complex of some fixed dimension. I'm going to do it in a similar way. There's actually 2 different ways to define a Markov chain, and I want to look at both. Is if I start with some subset of size k, then I can do exactly the same as I did before. I can drop one of its elements uniformly at random. This gives me a subset of size k-1. And then I can add back in an element with some probability associated to the mystery weight. And I can keep going. And if I take 2 steps in this, then this, so if I take 2 steps like this, then I've started with a subset of size k, and I'm outputting a subset of size k. I could also have started, I could run the same Markov chain, but start at a subset of size k-1 and take 2 steps like this. And this gives me a random walk on the subsets of size k-1. And because these steps are independent, you can think of the matrices for these 2 Markov chains as, one matrix the transition probabilities will have the form AA transpose, and the other will have the form A transpose A. this is roughly true. There's some asterisks on this statement, but this is roughly true. And so in particular, one can relate the eigenvalues of these two random walks, namely the random walk on subsets of size k and the random walk on subsets of size k minus 1. And even more so, as one can imagine from this picture, if k is not the top, if k is not d, then I can also do a walk going from subsets of size k to size k plus 1 and then coming back down. And somewhat remarkably, one can relate the eigenvalues of the transition matrix for all of these many walks that are going on. So not only this walk and this walk, but also the two walks on subsets of size k. And this was developed by many people and surrounding something called high-dimensional expanders. And in particular, one thing that one can show is, so if we're in this setup, you have a pure dimensional simplicial complex, and you have the following properties: that every link has a connected one skeleton, so some connectivity property, and also that the transition matrices on walks of one-dimensional links, so one should think of these as very small links. If this has a second eigenvalue at most 1, then the transition matrix on the top dimensional faces, which is potentially huge, like n choose d size matrix, that the second eigenvalue of this transition matrix is bounded away from 1 by 1 over d. So the second eigenvalue is at most 1 minus 1 over d. And this is really what comes from following from the technical details of this relation on eigenvalues. I'm not going to tell you. And in general, they prove a more complicated version of this. But the reason I told you this version is that it actually corresponds exactly to the generating polynomial of this simplicial complex being strongly log concave. And so in particular, this will hold for the independence complex of an arbitrary matroid. And so for any matroid of rank R, this gives a random walk on the bases that converges to the uniform distribution and mixes in sort of the order of R squared times log n steps. The complex can be weighted, and I'm not going to tell you about the weights. But let's take the weights to be 1. Just to answer a question in the chat. And this has been sort of generalized in various and strengthened in various ways since then.
There's about 2 minutes left, Cynthia.
Right. I'm just about done. And just to answer the talk from before, so this walk that I've defined is not exactly the natural random walk on the bases of a matroid, because the transition probabilities sort of have this funny dependence on how many bases like a basis minus an element has, but it's sort of close enough. In particular, using the Cheever's inequality that I started off with, is close enough to then prove that the edge graph of a matroid polytope has expansion at least 1. Yeah. So I see that I have a minute left, so I will just conclude that strong log concavity so encompasses many important examples. I didn't talk about it, but implies some nice discrete log concavity on the coefficients of a polynomial. and in particular has this nice connection with high dimensional expanders and can give distributions that can be efficiently approximately sampled with a Markov chain, on which a Markov chain will converge to its stationary distribution quickly. And here's a nice edge graph of a matroid polytope for you, and I will thank you for your time.
Thank you so much, Cynthia, for such a nice talk. Does anybody have any other questions for the speaker? So maybe while people are thinking that I was curious. Oh, go ahead. Please.
Oh, sorry for interrupting. I had a question. So I think in the theorem, you only need that, like, the polynomial for like the simplicial complex is log-concave, and that's implied by being like a matroid simplicial complex, whatever. But are there other examples like that don't come from matroids?
So for this specific statement, actually, so for polynomials like this, where all of the variables are square free, it's actually sort of the only way you can have a strongly log-concave polynomial, or indeed a log-concave polynomial, is if the monomials that show up are the bases of a matrix. And so in that sense, it's really an if and only if. If you allow higher degrees, then there's more. There are more possibilities. So Peter Vinzant and Jin He have this characterization of supports of strongly log-concave polynomials in terms of generalized permutahedra or M convex sets. So there are some other things out there. And actually, sort of in a different direction, this group also has considered sort of generalizations of this statement where they allow some flexibility in what numbers go in, and then you get different numbers out.
Okay, thanks a lot.
Perfect, thanks. Any other questions for Cynthia before we go into games with Vivian? Okay, if not, let's thank Cynthia one more time.